In this section, we will be studying about 8051 stack and subroutine instructions. We will also see some of the assembly level program examples based on subroutine and which involving loops. To have a small recap about the last session, we have seen what is stack in the previous section, and also we have seen what is a stack, which is a section of a memory which is used to store data or address temporarily. And also we have talked about a special function register called stack pointer, which holds the address of the stack memory. And we have seen what is push instruction and pop instruction, which is used for pushing or popping or storing or retrieving the data from the um, stack memory itself. And we have seen that the stack pointer will do a pre-increment use while doing push instruction, and a post decrement will happen during the pop. In this section, we will study two instructions which are used in a subroutine execution. These instructions are also dealing with the stack and stack memory and the stack pointers. We have already seen two instructions which are push and pop instructions in the previous section. So the other two instructions which deals with the stack memory are one is call instruction and one more is the return instruction. So this call instruction, there are two types, the long call and the absolute call. And as we know that the long call means the instruction, the subroutine, I mean, wherever the subroutine is residing, this subroutine can be residing in the span of 64 kilobyte, whereas absolute call means it can reside within a page. Within a page, as we know that a page is a memory of 2 kilobyte within the 64 kilobytes. A 2 kilobyte is called page. So within a page, this absolute call we can use if the subroutines are residing within that page, and long call we can use if the subroutine is residing in anywhere inside the 64 kilobyte of memory. And when it comes to return instructions, so return instructions are used after execution of the subroutine to return to the main program. We will use return instructions. So RET is the instruction which is generally used for subroutines. We have also a return of interrupt, that is RETI, which generally we will be using when it comes to interrupt service routine. So we will not be talking about the return of interrupts, RETI instructions in this section. So we will be studying about the call instruction as well as return instructions. And now when it comes to subroutines, you must be knowing what exactly the subroutines, if you are familiar with the C programming and all. We have functions in C program. So similar to that, we have subroutines in assembly level program. These subroutines are used to perform a task which need to be performed frequently. So this is to be noted that suppose we will just explain this with respect to some examples. So remember that if there are certain tasks which is to be performed frequently, then we will write subroutines for performing such tasks. So let us clearly understand this by with an example. Like now in this example, I have given one drawing here. You can see here. So assume that we have a main program. So I am going to write this main program in this block, and I am going to write my subroutine in this block. Okay. So when I say I am writing a program, you must be knowing that this program must be written in the code memory. So let me assume that my program is residing, the main program is starting from the memory location, the code memory location 0000 onwards. And assume, for example, my subroutine is lying in the memory location maybe F359. This is just a random memory location. So you don't need to worry where exactly you are writing the subroutine, which part of the memory you are writing the subroutine. That will be taken care by the IDE itself. So I'm just writing this as this memory just for a explanation purpose. You can also use org assembler directive to to initialize this location of the code memory. So if I write org 0f359h, and thereafter if I write my program, then this program will reside here. Similarly, to write the main program in the location 000h, I can write org 0. Okay, h is not mandatory because 0 is decimal or 0h is same. Let me take an example. Suppose I am writing this main program. Let me assume that this subroutine is a delay program. So I will be calling this as a delay subroutine. So delay is the what is that called, label which I am using to call this subroutine. So in this explanation, my main intention is to explain you how the stack pointer, how the program counter, and how the stack will change its values or behaves accordingly when you call a subroutine and when you come back or when you return from a subroutine program. And so I'm not giving much importance to the content of this main program or the subroutine. I'm only interested to explain the call function as well as the return function. So be aware about that. So let us assume that this main program is starting, as we said, it is starting from 000 location. So let there be some instruction written here. So there are few instructions written from here onwards. And maybe at some point, maybe at 000a, at this location 000a, I am writing a call function. So I will use lcall delay. So this is the call function which I am writing in the memory 000a. So remember 000a is the memory address of the instruction which is lcall delay. And remember, lcall delay is a 3-byte instruction. That means this lcall delay will take 3 bytes to store the code of the instruction itself. And so naturally the next instruction, whatever is the next instruction, which will be after 3 bytes. So 000A, 000B, and 000C will be occupied by the lcall instruction, and the next instruction will be residing in 000D. So this has to be understood. And so assume that your program execution is happening sequentially. So it executed this line first, then it is executing this line first, like that. It has come to this line, then it is executing this line. The moment it is executing this line, just before the lcall delay, if there is a line, that line, the moment it is executing, you must remember that the program counter will contain the address of, so PC, I will write it as, PC will be the address of the next instruction, which is lcall delay. That means PC will contain 000A. So that will be the content of the PC before executing this lcall instruction. The moment the lcall instruction is being executed, when this instruction is being executed, the PC content will change to the new address, which has to be 000D. This is what we are expecting, because the PC will always hold the address of the next instruction to be executed. So after lcall delay, the next instruction we are expecting, this is the next instruction, this line, and the address of that line is 000D. So we expect 000D to be residing in the program counter. But what happens is not this way. The moment lcall instruction is being executed, this new address of the subroutine, that is F359, will be loaded to the program counter. So program counter will get F359. That will be loaded to the program counter. And you know that this is a subroutine. So once the subroutine, whatever is the lines, I am not bothered. I said, so once the subroutine is executed, at the end of the subroutine, we have an instruction called RET. So when this RET instruction is executed, after this execution of this RET instruction, the program execution must come back to the next memory address, that is 000D, and start executing the remaining lines from here onward. So this is how the execution must happen. But so in order for that to happen, what are the changes happening in the stack pointer, what are the changes happening in the stack, etc. I will explain now. Now look at this. Yeah. So I will be now explaining the changes which is happening in the stack pointer, the stack, as well as the program counter, while calling the subroutine. So remember, as we have earlier seen, the program counter is now loaded with a 000A, which is the address of the lcall instruction itself. Wherever the lcall is written, that address is 000A. So the PC is loaded with 000A the moment the previous instruction to lcall is previous instruction to the lcall is being executed. So now the moment this lcall is being executed, what happens is, uh, remember, the default value of stack pointer is 07. Hence, the stack memory has to be 08 onwards. So 08, 09, 0A, like that, the stack memory. So now the stack memory is from 08 onwards. Now the PC contains 000A, as we have seen, and after the execution of the subroutine, the program execution should come back to the 000D location, that is the next instruction after the call instruction, right? So this address must be pushed to the stack. So that's the first task this lcall instruction does. So what it does is it will push the content of the stack. So 000D, so 0D will be stored in the lower stack location, that is 08 at stack memory, and 00 will be saved in the upper next stack. That means by the time a stack pointer will be incremented twice also, so stack pointer, once it pushes 0D, it will become 08, then it will become a 09. So stack pointer also will be incremented twice, and the values 0D and 00 will be pushed to the stack. So why 00 and 0D is pushed to the stack? Because that are the locations which the program should come back after the execution of this subroutine. And after this, what happens is, now PC has to be loaded with 000D after the execution of the subroutine. Now PC will change its content from 000A to F359. So this is what happens. So PC content will be now become F359. So that will be the new address of program count, new content of program counter. So naturally, when the PC contains F359, after the execution of this delay instruction, the program execution will change to this memory location, and at this memory location we have our subroutine written here. So we will complete the subroutine instruction number one, line number 1, 2. So keep on executing this, and at the end of this instructions we will be having the RET instruction written. And now what happens is, when we execute RET instruction, naturally you know that after the execution of this subroutine, this program control should go back to the location 000D. Why? Because that is the next instruction after the call instruction. So this 000D is already pushed to the stack. You can see it is already there in the stack. So what this return instruction does is it will pop the content of the stack, into the program counter. So program counter will keep changing its value based on the subroutine program's memory addresses. So once this is done during the return instruction time, what happens is the content of the program counter will change to 000D, and this program control will come back to the next instruction, which is 000D, whatever the instruction is written here, and the program will continue executing from that 000D location. So this is what is happening during the execution of the subroutine instruction. Let us understand this with the help of a program which is written using this Keel software. So we will see the live execution of that particular program and see how the program counter, how the stack and how the stack pointer contents, everything is being changing based on the call and return instructions. Through this program, I'm going to explain how the stack will work when it comes to subroutine programs, and I will also explain what happens during the call function and during the return function. So if you see, we have two section of programs in this. One is your main program, which is this highlighted one, line number 1 to 8. This is the main program, and there is a subroutine program which is spanning from line number 11 onwards. So we have a subroutine which is highlighted, and we have a main program. And in the main program, we are calling the subroutine two times. That is, in line number 4, we are calling it once, and line number 7, we are calling it again. So as we have seen, subroutines are generally used when we need to perform certain operations which are frequently appearing. So that's a reason why we are writing this as a subroutine, because here delay has to come frequently. Twice we are using a delay here in this main program. So instead of writing two delay section in this main program, we will write this delay as a subroutine, and that subroutine is been called. So coming to the disassembly window, you look at the disassembly window. Here it gives you a clarity about where the program resides in the memory location, that is the program memory or the code memory. If you see the main program, if you written here, it is starting from the memory location 0, because we have used an assembler directive org0 here. So you see the memory location, code memory C0x0000. That means the code memory location 0000. We are writing the first line of the code, that is move a comma 55. Yes, move a comma 55 is the first line. And thereafter move p1 comma a, we are writing in the next memory location, that is 0002. Yeah, since this first instruction takes 2 bytes of memory, that's why 0000 and 0001 is already occupied by the first instruction. So next instruction will be starting from 0002. So like that, you can see the disassembly window here properly. So let me make this disassembly window a little more compact, so that it will be easy for you to verify this code memory. So now if you see, as we know that there are three things we need to look into that. One is we have to see what is the content of the program counter. So you can see the program counter here, this highlighted one. So this program counter. And also when it comes to this call instructions, I expect you to check the stack pointer as well as the stack memory. So since the default value of the stack pointer is 07, the stack memory will start from the memory location 8 onwards. I already made this 8 available here. So this is 8, this is 9, and this is A, this is B, like that. Okay. So let us execute this program now. I am just using a step-by-step execution here. So let me execute the first line, that is move a comma 55. When I executed, the content of A is now changed to 55, because that is what is this instruction intended to do. And I will go to the next line, that is move P1. So I already enabled P1 here, and P1 was earlier FF. Now that is changed to 55. I mean 55H. So that is the thing. And now here comes the important thing. Like you see, the next instruction is lcall delay, and delay is a subroutine. And you look at this. Once again, I will come back here. And when you look at this delay subroutine, the code memory where this lcall instruction code is written is code memory 0004, and the current program execution is already done. That is the program which is residing in 0002, that is move p1 comma a, that's already completed. So that means the program counter, if you look at the program counter will store the address of the next instruction to be executed, and what the program counter now contains is 0004, and naturally 004 is the next instruction to be executed. So while executing this instruction, as per the definition of program counter, the program counter must store the address of the next instruction, which is again naturally move a comma 0x0a must be appearing. But look here, instead of going to the next instruction, we are now diverting or branching our execution to the subroutine, which is residing in the code memory 0. I mean, look at here we have defined this subroutine should reside at location 30F0. So let us go to that 30F0 and see whether it is there or not. Yeah, if I see the 30F0 location, this 30F0 location code memory, you have move R5, 0F, yes, move R5, 0FF, and after that F2 location DJNZ R5 again, and it will return. So this is the next, this is the subroutine. So we will just come back to the next line. This is yeah, our program execution is now happened in this second line. Now we will go to the third line and execute, and look, observe this. What should happen is this program counter is 0004 now, okay, and after execution of this delay subroutine, it should come back to this line, that is 0007. So now look at this stack pointer, which is now 07, and the program counter contains 0004, and the stack contains 0000 and 0000. Okay, now while executing the next line, what happens is we will just execute the next line. Now you look at this, the stack pointer is incremented twice. Why? Because the address 0007 is the address it has to come back after the subroutine. So this 007 must be pushed to the stack. Yes, the 0007 is now pushed to the stack. Stack is starting from 0008, that is this line. I mean, if I just put 8 here, you can see this 0007, it has to be read like that. So in 07 is the LSB of that address, which will be pushed first, then the MSB of that address 00, which will be pushed the next. So that what happens, and the program counter will load with the new subroutine address, which is 30F0. So once the subroutine is over, so what we will do is, let us assume that this subroutine, because this is a continuous program, so F11, which if you do it, that means it will take a lot of time to do it. So I will just run it up to this breakpoint, and yes, we have reached this line. And let us see, at this point the PC contains 30F4. 30F4 is the address of the return instruction, and while executing the return instruction, what naturally should happen is this 0007, which is there in the stack, must be loaded to the program counter. Let us see whether that happens or not. We will execute once again. Yes, And look at this. Yes, 0007 is loaded to the program counter and the stack pointer is decremented twice. It was 09 before and now it is 07. So this is what is happening with the subroutine instruction, and that this is how the address is being pushed to the stack when we are executing a subroutine instruction using a call as well as return instructions. So in order to conclude this section, we have seen instructions such as call and return in this section. A call instruction is used to call a subroutine, and a subroutine are often used to perform tasks that need to be performed frequently. This creation of the subroutine makes the program more structured in addition to saving the memory space. There are two types of call, that is L call and A call. L call is a 3-byte instruction, and in this 3 byte, the first byte is the opcode and the next 2 bytes are the addresses. So we have totally 3 byte. This is 1 byte and this is 2 byte. So it's a 3-byte instruction, and the subroutine can be located in case if you are using lcall, the subroutine can be located anywhere within the 64 kilobyte of the memory space. That's about the L call. And when it comes to absolute call, that is A call is a 2-byte instruction. A call, which is a 2-byte instruction, and this instruction is this when we are using this A call instruction, make sure that this subroutine is residing within a page, okay, within a 2 kilobyte space, memory space. That's a page. So that's about the absolute call. Remember that when a subroutine is called, the control is transferred to that subroutine, and the processor saves on the stack the addresses of the instruction immediately below the lcall instruction, and it begins to fetch the instructions from the new location. After finishing the execution of the subroutine, the return instruction transfers the control back to the main program, and every subroutine needs a RET instruction at the end, at the last instruction.